Hello. In this video, we're going to look at second-order equation theorems. Let's jump right in with the second-order differential equation version of existence and uniqueness. Given the initial value problem, y double prime plus p of t y prime plus q of t y equals g of t, where y of t naught equals y naught and y prime of t naught equals y naught prime. Where P, Q, and G are continuous on open interval I. I that contains T naught. All right, so given all this, given initial value problem, has this structure, initial conditions, P, Q, and G are continuous on an open interval. Assuming we have all that, then there is exactly one solution y equals phi of t, and the solution exists throughout interval I. Okay, so that's our theorem. What does it say? What does the theorem say? What's the important information that's in there? Okay, well, if you read it carefully, it says, as long as we have continuity in P, Q, and G, then the initial value problem is guaranteed to have some stuff, right? So let's actually just write that down. So as long as we have continuity, what happens? As long as P, Q, and G are continuous, what do we get out of that? Well, we get that there is a solution. So we get existence. We know that we will have a solution. Right? What else? There is exactly one solution. So we get uniqueness. And then finally, we get that the solution exists throughout interval I. So we get the location of the solution. Okay, so that's our existence and uniqueness theorem for second order differential equations. It's similar to the first order definition, right? So the main thing that we need throughout all of these different theorems is that we need the functions that are contained within them to behave well, right? To be continuous, right? Discontinuities are where things like integrals break down. And if you're going through and solving a second order differential equation, you have to go through and integrate. All right, so let's go through and apply the theorem just like we did in previous videos. Find where the unique solution exists. For the following problem. All right, so we've got our initial value problem. If we're going to go through and use the theorem, the first thing that is critical is that it has to have the same format as the theorem. Notice that the format of the theorem does not have a function that's multiplied by y double prime. So we do need to go through and move that function over by dividing it out. So if we divide everything by t squared minus 3t, we will get y double prime plus t over t squared minus 3t minus t plus 3 over t squared minus 3t times y equals 0. Now that it's in this format, we have here's p, here's q, here's g. So we need all of those to be continuous in order to guarantee that we have a unique solution. All right, so what's going to prevent this function from being continuous? Well, the places where the denominator could be 0. So 0 and 3 would both make the denominator 0. So we have discontinuities at 0 and 3. How about here? Same thing, right? Discontinuities at 0 and 3. And then we don't get anything from G. Okay, so in terms of where is this thing going to be continuous, what we can do is we can go through and just kind of create a little number line for ourselves. So here are where the discontinuities are. What that does is it breaks up the number line into the regions where we have continuity, where all of the functions are continuous. So less than 0, both of the functions p and q will be continuous. Between 0 and 3, they'll be continuous. And 3 and above, they will be continuous. Okay, so once we've done that, the only thing that's left is that little bit that I almost didn't write, and that is that they're continuous on the interval that contains t naught, right? So t naught, that is critical in going through and deciding which of our intervals we would use to guarantee a unique solution to this initial value problem. Well, if you take 1, so where is 1? 1 is in this interval here. Right, if you just break these up into intervals, 1 lies in this middle interval, and so that's going to be the answer. So find where the unique solution exists. It exists from t from 0 to 3. Okay. And so that's how you'd go through and handle these types of problems where they ask where the unique solution exists, is go through, get y double prime by itself, identify functions p, q, and g, find out where they are discontinuous, thus implying that they're continuous everywhere else, mark the places where they're discontinuous, and then you can go through and use the initial condition to determine which of those regions is going to be the right one. For this initial value problem, right? If you change the initial value problem and we had different initial conditions, then we could end up with the other regions as the answer. Okay, so the rest of the section is mainly concerned with going through and handling theorems that are related to having two solutions. Okay, so we've talked about some of these theorems before in maybe little bits and pieces, skimmed over them. And so what we want to do is we want to cover them in more depth, make sure that we look into all of the details, and just make sure that we have a thorough understanding of the effects of having two different solutions to a differential equation. Okay, so the first theorem that we're going to look at is the theorem of the principle of superposition. So we've been using this one. What does this one say? It says, if we have two solutions, then are we guaranteed to have all the linear combinations as solutions? So let's just write that out. So if y1 and y2 are solutions, of the differential equation y double prime plus p of t y prime plus q of t y equals 0, then c1y1 plus c2y2 is a solution as well for any c1 and c2. So we've been using this solution in previous videos. In previous videos, we'd go through and we'd find a solution to the differential equation. We'd find a second one, and then we would go through and say, well, if these two solutions work independently, then we can go through and take linear combinations of them, and they will also work. And we provided some evidence in those videos for why that is, but this will go through and prove that that's true in general, rather than just the specific situations that were in those videos. This will prove that it's true for all second-order differential equations that have this format. Okay. So how do you go through and prove this? Right. So what it's saying is that we have y1 as a solution, we have y2 as a solution, and then it's saying that the linear combination is a solution. All right. So to go through and prove the linear combination is a solution, all you've got to do is just take it and plug it in. All right. So if we take it and plug it in, watch what happens. We'll have c1 y1 plus c2 y2, and we're plugging it in. So we're going to put it in place of the y. So we're going to have double prime plus p of t times c1 y1 plus c2 y2 prime plus q of t times c1 y1 plus c2 y2 equals 0. Okay, so if this is a solution, right? So if y1 and y2 are solutions, then if it implies that this is a solution, then when we go through and solve this, we should end up getting that this is true. We should end up getting that we get 0 on both sides. Okay, how do you do that? All right, so derivatives, what do we know about derivatives? We know they distribute over addition, and we know that you can factor out scalar multiples, and so we know that we could rewrite this as c1 y1 double prime plus c2 y2 double prime. And then here we could do p of t and c1 y1 prime, c2 y2 prime. And then here, let's just go ahead and distribute with us. So we're going to have C1, let's do Q of T y plus C2 Q of T y, y1 and y2. All right, let's go ahead and distribute this out as well. So we'll have C1 y1 double prime, C2 y2 double prime. We'll have C1 P of T y1 prime, C2 P of T y2 prime, C1 Q of T y1, C2 Q of T y2. And then what we're going to do here is we're going to go through and group things up. We'll group up all the C1s, and we're going to go ahead and just to speed this up, we're going to go ahead and factor out the C1 at the same time. So what do we get? We'll get C1, and then we're going to have y1 double prime, and then C1, and then the C1's pulled out, and then we'll have P of T y1 prime, and then Q of T y1. And then here we'll have C2, and we'll have y2 double prime, and then we'll have P of T y2 prime, and then we'll have Q of T y. All right, and so going back again to the theorem, what does it say? It says y1 and y2 are solutions. What does that mean? That means if you took y1 and you plugged it in, it'd make the differential equation true. In other words, y1 double prime plus P of T y1 prime plus Q of T y1 would equal 0. Okay, well, if that's true, that's what is written exactly right here. So we have C1 times 0. And that y2 is also a solution, meaning you could plug it in, it would make the differential equation true. Thus, y2 double prime plus P of T y2 prime plus Q of T y2 would equal 0. Well, if that's true, that's what's written right here. So we could replace that with 0. Okay, and so if you've got C1 times 0 plus C2 times 0 equals 0, then you know that you're going to get 0 equals 0, no matter what C1 and C2 are. So for any C1 and C2, it does not matter what C1 and C2 are. You could literally pick any numbers, and since you're multiplying them by 0, you're going to end up getting 0. And that proves the theorem. Okay, so, and again, what does that specifically say? If we have two solutions to the differential equation, then we're guaranteed that all the linear combinations will be solutions, right? So if you've got 1, 2, then linear combinations will also always be solutions. Okay, so that's the first easy, simple proof. Regarding two solutions, what's next? All right, so the next theorem gets into if we have two solutions, when are we guaranteed that the solutions are different enough to satisfy the initial conditions? Okay, so let me just talk about that more in a second after I write the theorem down so that you can kind of see what the theorem is getting at. So suppose y1 and y2 are solutions to y double prime plus P of T y prime plus Q of T y equals 0, and that we have initial conditions. Y of T naught equals y naught, and y prime of T naught equals y naught prime. So we've got some initial conditions. Then it is always possible to find a C1 and a C2 such that C1y1 plus C2Y2 satisfies the differential equation and the initial conditions. If and only if W equals y1, y2 prime minus y1 prime, y2 is not 0 at t0. This thing is called the Wronskian. Okay, that's a beast of a theorem with a lot of words. So what is it saying, right? So it's saying that we go through, we find two solutions to the differential equation, right? We go through and we find y1, we find y1, we plug it in, it works. We find y2, we plug it in, it works as well. We have initial conditions, that we have two initial conditions that are defined. Now the question is how do we know whether our two solutions that we found, how do we know whether those two solutions are going to enable us to go through and solve the differential equation with the initial conditions? You might assume, well, why wouldn't it? Why wouldn't it? Well, here's the thing, right? So two solutions, what if the two solutions were the same solution? Right? So if you recall from our previous videos, every single time we've gone through and we've solved a differential equation, we've always gone through and said we have two solutions that are very different. And using those two very different solutions, we assumed we could go through and solve the differential equation. And we never ran into any problems in the previous video. So you can go back and just watch them. We went through and we solved, those homogeneous linear second order differential equations with constant coefficients. We went through and we solved those. We came up with two solutions. We solved initial condition problems. We never had any trouble. Well, the reason that we never had any trouble is because our two solutions were very different. What if those two solutions were not very different? What if they were the same solution, right? Just imagine you're going through and you go back to the first video that we solved where, we were going through and we were solving a differential equation. And, what if we had said, we're solving y double prime minus y equals 0. That's the first one that we did. And we said e to the t was a solution, right? So what if we said our two solutions were e to the t and e to the t? They were the same solution, just listed twice. Would those two solutions have been different enough to satisfy any initial condition? The answer is no. We could have made up initial conditions for that problem, and then those two solutions, which are the same solution, would not have been different enough. We would not have been able to solve the initial conditions. So it would have been possible to create initial conditions that would not have been solvable with such a simplistic solution, right? We need to have enough variation. We need to have enough difference, enough complexity in our solution to enable us to go through and solve for the two initial conditions, right? Two, because we don't have one, we have two. Okay, and so this theorem is all about establishing a test to determine how different do the two solutions need to be so that we are guaranteed that we can go through and solve an initial value problem, a differential equation with initial conditions. How different do the solutions need to be so that we're guaranteed to be able to solve it? All right, and that's what the theorem deals with. That's what it discusses. And what it says is that we will always be able to find a C1 and C2 that satisfy the differential equation and the initial conditions. We'll always be able to find something that has this format that solves the initial value problem as long as this thing here is not 0, this thing called the Wronskian. Okay. And then we have an if and only if, right? So that tells us that we could go both ways logically. All right. So if it's always possible that C1 and C2 can be chosen, then that implies the Wronskian is not zero. And if the Wronskian is not zero, then that implies that we can go through the other way. So we have we have both directions logically, right? I can't remember whether we've discussed if and only if previously in this video series, but if not, then it's something to go through and Google. We're going to prove it both ways, kind of. We're going to cheat, but just to be clear, the way in which we're going to prove it. Well, actually, let's just get into the proof, and then I'll talk more about it. Okay. So what do we have? What information do we have to go through and prove this? Well, the information that you have is important to understand where the line is drawn. All of these are kind of the initial part, and then this is the second part of the proof, right? So we have this, we have a differential, we have two solutions to a differential equation, and we have initial conditions that are defined. And then this is all part of the if and only if. This big long statement is, precedes the if and only if, and then the consequence is this statement here. All right, so we're going to first suppose that we have all this stuff. All right, so suppose y1 and y2 are solutions. Well, we'll say they satisfy. That's what I wrote in my notes. They satisfy y double prime plus p of ty prime plus q of ty equals 0. And we have initial conditions y of t naught equals y naught, and y prime of t naught equals y naught prime. All right, so if you go and look at the theorem, that's what was written right here. So we've written down the information that we're given. Now to go through and do the proof, okay, what we're going to do is we're going to do an if and only if. That means that this, we can say this, if this, then it implies this. Or we could say if this, then it implies this, right? The if and only if means that the logic goes both ways. So what we're going to do is we're going to go through and we're going to start with this statement as true and see if we can work our way to the second statement, and then proving it the other direction. We're going to cheat. I'm going to cheat to do that part. All right. So want to go through and write down the rest. So what is that long statement that we can suppose now? We're going to suppose it is always possible to choose a C1 and C2 such that y equals C1 y1 plus C2 y2 satisfies the differential equation and the initial condition. And the initial conditions. Okay. Now we've got all of our information. We've got this part of our supposition. We've got this part, and now it's our job to go through and logically manipulate what the information we've gotten into this alternate form. If we've done that, we'll have proven the if and only if one direction. Okay, so how do we do that? Well, since we know that this y equals C1 y1 plus C2 y2 satisfies the differential equation and the initial conditions, that means that we could take the initial conditions, the T naught, and we could plug it into this, and it should produce y naught and y naught prime. So we can go through and say that C1 Y1 of T naught plus C2 Y2 of T naught equals Y naught, right? So I'm taking T naught, plugging it into this thing, which we say satisfies the initial condition, so it should make this true. We should be able to plug T naught into this, and it should give us Y naught. And now we're going to do the same thing with Y prime. So we're going to have C1 Y1 prime at T naught plus C2 Y2 prime at T naught equals Y naught prime. Okay. So it may not look like it at a glance, but this is in the form of a system of equations. Now there's a lot of symbols there, so let me explain that, right? So we're supposing Y1 and Y2 satisfy this thing and that we have these initial conditions. So these initial conditions, what are they? Well, T naught is a number. Y naught is a number. T naught number. Y naught prime is a number, right? So Y1 of T naught, that's a number. That's Y naught, okay? Well, hold on, that's not Y naught. Sorry, the combination is Y naught. Y1 of T naught is a number. You're just taking T naught and you're plugging it into your function Y1. You've got a number here. You've got a number here. You've got a number here. A number here. A number here. A number here. The C1 and C2 are the only things that are unknown here. We know it's possible to choose a C1 and C2 so that this equation is satisfied. Okay, but C1 and C2 are not given. We don't know what they are. Well, we know what everything else is. This is a number, that's a number, that's a number, that's a number, here's a number, here's a number. So we just have a bunch of numbers there. So this is a system of equations where we know it's possible to find a C1 and C2 that satisfies it. Okay. So next, and I should have mentioned this earlier because that was my intention actually to bring this up earlier in the proof. This proof is going to rely upon linear algebra. If you have not taken linear algebra, if you're in linear algebra right now, then you probably have enough knowledge to be able to do this. But if you've not taken linear algebra, then at a certain point in the proof, it's just going to go off the map. It's just going to be like, wait, what? What's going on here? And that's just the way that it is. Differential equations has linear algebra content in it. You really need to have taken or be in a linear algebra class while you're taking differential equations to understand parts of it. Okay, can you understand the broad topics in differential equations without linear algebra? Yes, but there's going to be proofs that you don't understand, and then actually later on in the course, you're going to run into a serious problem. But immediately you're going to see we're going to jump into linear algebra right now. So I'm going to take this system of equations and I'm going to rewrite it into the form of a matrix equation. This is a common thing to do in a linear algebra course. All right, so what is our matrix equation? We have y1 of t naught, y2 of t naught, y1 prime of t naught, y2 prime of t naught, C1 and C2, y naught prime. Okay, this statement is still just kind of inherited. It's still there too. We have our matrix equation now, and our matrix equation, again, this is all numbers here. These are all going to be numbers when you actually, if you actually had a real situation. These are all numbers. These are all numbers, and C1 and C2 are the unknowns. And we know, we're guaranteed that a C1 and a C2 exists that solves the system. It's always possible to choose a C1 and C2 so that will satisfy this system. Okay. The next thing that we're going to do, we're going to continue off into linear algebra land. We're going to go ahead and we're going to call this thing A. We're going to call this thing X. I'm going to put a bar over it to represent the fact that it's a vector. And we're going to call this thing B. Okay. And what I'm going to do is I'm going to take this statement and I'm going to try and translate it into language for this new A. Let me move the A over so it's a little closer to the X. It's like hanging out over there by itself. AX equals B. So I want to try translate this. So what this is saying, this is saying that AX equals B, that we're going to be guaranteed to be able to find an X so that AX equals B is true. All right. So if this matrix, if this equation here, we know that a C1 and C2 exists that will solve this, then when we rewrite it into this form, we know that an X exists that will solve this. In other words, this is the way I'm going to translate it. AX equals B has a solution X for any B. Any B, right? So that is a slight change in terminology. I mean, what we've been saying is we've been saying that there's always a C1 and C2 that will satisfy this equation. And you'll see I went from AX equals B has a solution. We're guaranteed to have a solution for any B. So what is the any B? Where does that come from? Well, so if you kind of go back to our initial conditions here, what that any B is saying is that it doesn't matter what Y naught and Y naught prime are chosen, that we could choose any Y naught and Y naught prime, and yet it will still be possible to choose a C1 and C2 that satisfies this. So the any B part is really just focusing, is drawing more attention to the Y naught and Y naught prime part of the statement here, but it still does fit together, right? If you suppose Y1 and Y2 satisfy this, and we have initial conditions, the initial conditions are not, if it's not specified, it's implied that they would work for any initial conditions, for any Y naught and Y naught prime that would satisfy this. So this kind of jiggering of the language is not intended to deviate from the proof. It's just intended to go through and restructure into linear algebra language. And so this really is logically the same thing as these previous statements. It's just written slightly differently. So why do that? Why write it this way? Why not say AX equals B has a solution that we know a solution X exists that solves the system? Why not just keep using this terminology or this language? The reason for that is if we're going to go into linear algebra land, which is where we're deviating into, we need to use the terms from linear algebra. And this term in linear algebra is important if you've taken a linear algebra course. This is one of the equivalency statements in linear algebra, which is a critically important part of a linear algebra course. All right, so this is an equivalency statement. And what equivalency statements do is it opens the door to other statements that are equivalent. And so we're not going to use that fact to move the proof forward. Maybe that's the best way to put it, to move the proof forward in the direction of what we want to accomplish, which is showing that this Wronskian thing is not equal to 0. All right, anyway, so we've got this equivalency statement. What does the equivalency statement get us? Okay, so a statement that's equivalent to that is that the determinant of A is not equal to 0. All right, so this is a statement that it's equivalent to the previous statement. And if you're looking at that and you're saying to yourself, wait. So if ax equals b has a solution x for any b, and then I can just jump to just saying that the determinant of a is not equal to 0. Where does that come from? That's what I'm trying to tell you. It comes from the equivalency statements in a linear algebra course. If you've taken linear algebra, then that's something that you should know, that those two statements are equivalent, that you can take this, if you've got this statement, if it's part of a proof, if it's part of some logic, it's part of some argument, you can just immediately just jump to this other statement that they are equivalent. And in a linear algebra course, you'd go through and prove that. You'd prove that those two statements are equivalent and that you can just make that logical jump because the two don't seem to be connected at all. And if you're not familiar with DET, this stands for determinant. Again, that's another thing from a linear algebra course. And so anyone who's taken linear algebra should know what that is. Okay, anyway, let's just proceed. I don't want to dwell too much on the linear algebra stuff because if you don't know linear algebra, you haven't taken it, then you're just sitting there being, okay, well, cool, thanks. I don't understand the proof. And so let's just get it over with. All right, so what is A? Well, so the determinant is going to be the determinant of the matrix A. What was A? A was this, right? That was A. That's where we got A from, right? This was X. This was Y naught prime was B. C1, C2 was X. And this thing was A. So we get Y1 of T naught, Y2 of T naught, Y1 prime of T naught, Y2 prime of T naught. So determinant of A is not equal to 0. Thus the determinant of this is not equal to 0. And then what is the determinant of this? It is Y1 of T naught, Y2 prime of T naught, minus Y2 of T naught times Y1 prime of T naught is not equal to 0. And that was what we wanted to prove. That the Wronskian, which is this thing, is not 0 at T naught. Not 0 at T naught. All right, so Wronskian, not 0. That the proof one way is complete. That's the whole thing, right? So let me recap it for you, right? So once you start off, you've got this information. We go through and we say, all right, so we're going to suppose it's always possible to choose a C1 and C2 such that this statement satisfies the differential equation and the initial conditions. That means you should be able to take T naught, plug it into this, and it should make the initial conditions true. So we did that. We took T naught and plugged it into this, and it should get you Y naught, and it should get you Y naught prime. And based upon this statement, we should always be able to find a C1 and C2. So this is true regardless of what Y naught and Y naught prime are. From there, you take it and you rewrite it into a matrix equation form. Okay, so that's just a basic step that you can do. So we restructure it into this form. So that doesn't change anything. There's no real logic there. It's just a restructure. And then from there, as we discussed, we could take this and we could rewrite this statement here. We could rewrite it in terms of just slightly different wording into this statement. And that gets us one of the equivalency statements, which enables us to jump to another equivalency statement, which basically, boom, gets us the proof. So the proof is really because of the equivalency statements in linear algebra. That's where it comes from. So why is this true? Because of that. All right, so that concludes the proof in the direction that we initially discussed. So we've got the if and only if here. So with the if and only if, it means that if this is true, then this has to be true. We just proved that. However, an if and only if also means that if this is true, then this has to be true. So we have not proven that. How do you go through and prove that? Okay, so here's where I'm just going to cheat, right? So if what we have is we have that the Wronskian is not 0, and what we want to get to is this statement here, well, start off, the Wronskian is not 0. That means that this is not 0. That means the determinant is not 0. That means the determinant of A is not 0. That means that AX equals B has a solution for every B. That means we could go through and take AX equals B and rewrite it into this form. That means we could rewrite it into the system of equations form. And that means that we could go through and say that, and make this statement. Suppose that we could always say that it's always possible to choose a C1 and a C2 that satisfies the differential equation in the initial conditions. So this is not unusual in an if and only if proof, that if you prove it one way, then proving it the other way is just reversing the logic, where you could start here at the end as your first statement and just go the other direction. So that's what we're going to do. It's a little bit of a cheat, but that's what we're going to say, is we're going to say that we actually have proven it both ways by just reversing the logic. Okay, and so that concludes the proof. All right. Okay, so now that we've finished that up, what we've now got is we now have a test, and that is if we have our two solutions and we want to know, are they different enough to satisfy the initial conditions, we could go through and calculate the Wronskian at the input of the initial conditions at T0, and that will go through and it will tell us whether the two solutions we have are different enough to satisfy any two initial conditions. Okay, so where do we go from here? The next theorem is going to get into, if we have two solutions, are those two solutions different enough that we have all of the solutions to the differential equation? All right, so let's write that out and then we'll talk about it for a second. Hold on. So we've got theorem. Suppose y1 and y2 are two solutions to y double prime plus p of t y prime plus q of t y equals 0. Then the family of solutions y equals c1 y1 plus c2 y2 with arbitrary c1 and c2 includes every possible solution of the differential equation if and only if there is a T0 where the Wronskian of y1 and y2 is not 0. Okay, so what does that say? That theorem sounds kind of similar to the last one. They are not the same. They are actually very different, right? So consider, what does it mean to solve a differential equation? It means that you find the function that you could plug into the differential equation that would make the differential equation true. Okay, that's what it means. It means that you've got your function that you could plug in and it would make it true. So what this theorem deals with is, it deals with, if you've got two solutions, if you've got y1 and y2, you've got two things that you could plug in and will make it true. Two things, two functions. So we've got two functions that you could plug in that would make it true. If we went through and took linear combinations of those two things, those two functions, then does it include every possible function that you could plug in that would make the differential equation true? Okay. Now, if your assumption is, well, why wouldn't it? Well, it's for a similar reason to the example that we gave for the last theorem. So the theorems are different, but the example that you give would be similar, right? If you go back to any of the homogeneous linear second order differential equations with constant coefficient problems that we have solved in previous videos, in all of them, we had two solutions that we went through and we said that we took linear combinations of and that it got us all of the solutions. That's what we did, right? We had our section where we had two different solutions, R1 and R2, and we said C1 e to the R1t plus C2 e to the R2t. That got us all the solutions. Well, if you're just assuming, well, why wouldn't it? Well, what if someone went through and solved that and said that e to the R1t, if they just gave you that twice and said, is that going to get you all the solutions? The answer is no. There could be an e to the R2t. There's an e to the R2t out there that you haven't found. So just because you find two things, just because you find two functions that you plug into a differential equation that make the differential equation true. Let me restate that. Just because, and write it here. Just because you find two things, two functions, just because you find two functions that you can plug in the differential equation that would make it true does not guarantee that the linear combinations get you all of the solutions. Right? That is not true. Now, if you're sitting there and you're saying, wait, but I watched the previous videos, and in the previous videos, you found two different solutions, and you just assumed that those two were sufficient to get all of the solutions. And to that, the answer is you're dead on. That's right. In those videos, we did assume that, and in this video, we're going to go through and we're going to prove that we were right to. But at that time, you know, there would have been reasonable doubt that we had found all the solutions by just finding those two, right? So what this theorem deals with is, are the two solutions that you found, are they different enough to get you all of the solutions? So that you know that there's no function that you're going to stumble upon, later down the road that you could plug in and that would work in the differential equation that's not in the combinations that you've already found. How do you guarantee that will not happen? And that's using this theorem. All right, so using this test. So we have a test for that. We can go through, and if we've got two solutions, we can go through and we can test to determine whether they are different enough to get us all the solutions. All right, so let's prove this. All right, so what have we got? We have, suppose y1 and y2 are two solutions. To y double prime plus p of t y prime plus q of t y equals 0. Suppose there is a t naught where the Wronskian is not equal to 0. Hold on. The Wronskian of y1 and y2 is not 0. And then finally, we're going to suppose a third thing here. Suppose y equals 5t is any solution. You could think of it as an arbitrary solution. You grab a solution to y double prime plus p of t y prime plus q of t y equals 0. All right, so let's just check and see where we're at as far as the proof. Okay, so here's our theorem. Suppose y1 and y2 are two solutions. Check. All right, and then after that, we have then the family is guaranteed. Let's just put some parentheses around this. Then the family of the solutions with arbitrary C1 and 2 includes every solution of the differential equation if and only if there is a T naught. Right, so this is the if and only if again. And the way the if and only works, if works, it means that the logic, you could have this statement. If we have this statement, then we're guaranteed that this statement is true. And also, if we have this statement, then we're guaranteed that this statement is true. And so what you could see with my proof is I've started off with this supposition before we got into the if and only if, and I wrote that. And then the next thing I wrote is I wrote this part. So I'm assuming this part is true, and then I'm going to go through and work to this part. So I did not, you don't have to do if this is true, then this is true. You could start with this one first and then prove the direction the other way. You could start with the only if part first and then go to the if part. And so that's what I'm doing here is I'm starting with this piece. So that's why I have the whole thing with the Wronskian here is I've got the second part. And now this last part, suppose y equals 5t is any solution. That's just, we're going to need that for part of the proof. All right. And then so our goal is going to be to show that this last part, that y equals 5t is in C1 y1 plus C2 y2. That's effectively the other statement. The other statement is that then the family of solutions, it includes every solution. So if I go through and I say, hey, I'm going to suppose I've got a solution, then what does that has to happen for this piece to be true? That solution has to lie in C1 y1 plus C2 y2. Right? Does that make sense? So, and the family of solutions contains every solution. So if you've got a solution, then it's got to be in the family. And so that's where we're at. We've got our suppositions here, and then we need to show that this is in the family. All right, so how do we do that? So we could say, since phi of t is a solution to y double prime plus p of t y prime plus q of t y equals 0. And we know that T naught can, if you plug it into the Wronskian, if we've got T naught that we could plug into the Wronskian where y1 and y2 are not 0, we could take that T naught and plug it into phi of t here and get y naught equals phi of T naught and y naught prime equals phi prime of T naught. Okay, so since this is a solution, that means it's got to satisfy the differential equation. And since we know that T naught works in y1 and y2, which also satisfy the differential equation, that means we could take T naught and we could plug it into phi and generate some initial conditions. Okay, so once you've done that, the next thing we can say is we can say, thus, y equals phi of t is a solution to the initial value problem that we just created using those initial conditions. Oh, hold on. Right? So if phi satisfies this and it satisfies the initial conditions, then it satisfies the initial value problem that is the two together. Okay. All right, so next we're gonna have to go to the next page. But the next thing that we're gonna do is we can go through and say we're gonna use the Wronskian part now. So since the Wronskian at T naught is not equal to 0, then the previous theorem that we just finished solving, that we just finished looking at, let's just go back to it. What does the previous theorem say? If the Wronskian is not 0, then we're guaranteed that C1y1 plus C2y2 satisfies the differential equation and the initial conditions. So we're just going to write that now. All right, so since the Wronskian of y1 and y2 is not 0 at T naught, we know that C1y1 plus C2y2 satisfies the differential equation and the initial conditions. That's literally just copied from the previous proof. Right, so thus C1y1 plus C2y2 is a solution to the initial value problem. Y double prime plus P of Ty prime plus Q of Ty equals 0. Y of T naught equals Y naught. Y prime of T naught equals Y naught prime. Okay, so what have we got there? So we've gone through and we've said we have y equals phi of t as a solution to the initial value problem, and we have C1y1 plus C2y2 is a solution to the initial value problem. Okay, to the same initial value problem. That is critical, the same initial value problem. All right, so thus phi of t and C1y1 plus C2y2 are solutions to the same initial value problem. Well, what do we know about solutions to initial value problems? Well, you might think, well, we don't know anything. What do we know? What are you talking about? What do we know about them? Well, let's go all the way back, all the way back, all the way back. Go in the way back machine here. Given an initial value problem where P, Q, and G are continuous, then there is exactly one solution for the initial value problem. Exactly one solution, right? If we go through and we have found how many solutions? How many solutions? We have 2 solutions to the same initial value problem. What does that mean? What does that mean if phi of t and C1y1 plus C2y2 are both solutions, right? Well, so based upon the uniqueness of solutions to initial value problems. Phi of t has to equal C1 y1 of t plus C2 y2 of t. Right? If you have two solutions and you know that there's only one, then those two solutions have to be the same solution. Okay, so what does that say? Right? That says if phi of t has to equal C1 y1 plus C2 y2, then phi of t is in C1 y1, right? So thus phi of t is in the family and that completes the proof. Okay, what does the proof say? The proof says that given y1 and y2 are solutions, then the family of solutions contains all the solutions is equivalent to, if and only if the Wronskian is not zero. So what did we do? We started with the Wronskian is not zero, and we needed to go through and show that an arbitrary solution is going to be in the family. So that's what we did. We went through, we started with the Wronskian. We went through and just said, suppose we've got any old solution, an arbitrary solution, we just grab one. If we can just grab one solution, we can show through logic by manipulation that that one solution has to lie in the family, and that completes the proof. Okay, it completes the proof one way of the if and only if. This is another one where the if and only if can be just reversed, right? So if you go through and you start off, it's in the family, right? If it's in the family, so phi is going to be in the family, thus you can go through and say that phi equals this, thus you could go through and split it apart, right? And you can just work your way backwards all the way to the beginning and to showing that the Wronskian is not zero. So you can just go back upward until you get to the Wronskian is not going to be zero. All right, so that ends up going through and completing the proof of the theorem. Okay, so what does that leave us? It's important to kind of make sure that we understand the consequence of these things. What's the result? The result of that last theorem is that if we have two solutions and the Wronskian of the two solutions is not zero, then the linear combination represents all solutions. All right, so if y1 and y2 are solutions, to a differential equation, y double prime plus p of ty prime plus q of ty equals 0, and the Wronskian of y1, y2 is not equal to 0, then c1 y1 plus c2 y2 represents all the solutions. Right? Thus, we would call it the general solution. And that's what we've been calling it so far. So that, when we've go through and solved differential equations, so thus it is the general solution. To the differential equation. And then we're going to introduce some new terminology, which will come up later on. And that is that y1 and y2, we're going to give them a special name, the solutions y1 and y2 are called a fundamental solution set. Is there more than one fundamental solution set to a differential equation? Absolutely. There are an infinite number of fundamental solution sets. Okay, so just because you found two solutions do not mean that you found all of the fundamental solution sets. You can go through and find other pairs of solutions that you could go through and use to get all of the solutions. All right, so for the last bit of this this video, what we're going to go through and do is we're going to prove that in all of those previous sections where we found two solutions to the differential equation and then claimed that we had found all of the solutions and wrote that as the general solution, we're going to prove that that was okay to do. We're going to prove that we're going to retroactively, we're going to go through and prove that that was fine. All right, so let's go ahead and do that now, and that will finish things up. All right, so in what videos did we do that? Well, so in what we said at one point is that the general solution to y double prime, or sorry, ay double prime plus by prime plus cy equaled 0 when the characteristic equation had two real roots R1 and R2 is y equals c1 e to the r1t plus c2 e to the r2t. All right, so we claimed that previously, that the general solution to ay double prime plus by prime plus cy equals 0 when the characteristic equation had two real roots was y equals c1 e to the r1t plus c2 e to the r2t. We claimed that. We claimed that that was the general solution and that we were good to go. That these two solutions were different enough that we had all the solutions. And I want to be explicit here. The two solutions here, this is y1 and this is y2. So this is in the form of c1y1 plus c2y2. We said that linear combinations of e to the r1t and e to the r2t got us all of the solutions. Well, let's go through. Are those two different enough that we will get all of the solutions? Let's calculate the Wronskian. All right, so the Wronskian of y1 and y2 equals, it's the determinant of the 2 by 2 matrix, where we have y1, y2, y1 prime, y2 prime. So that's going to equal, all right, so y1 is e to the r1t, e to the r2t. The derivative of y1 is r1 e to the r1t, r2 e to the r2t. The determinant, the way determinants work, you multiply this by this and then subtract this times this. So we're going to get r2 e to the r1t e to the r2t. That's this times this, minus r1 e to the r1t e to the r2t. That's minus this times this. And you can rewrite this. This is r2 minus r1 times e to the r1t plus r2t. And the question is, for the Wronskian to tell us that we have enough difference between our two solutions, that we have all of the solutions, we have to be able to go through and say that the Wronskian is not 0, not 0. Is this not 0? Well, what do we know? Well, what do we know about e to the r, e to any power? Well, we know e to the any power cannot be 0. Exponential functions never equal 0. And so the question is, can this be 0? And if you look at this, you say, well, it could be 0 if R1 equaled R2. Can R1 equal R2? All right, well, I guess maybe I should have been more explicit in my my definition here. Two different real roots, right? Different is implied in here, not the same two real roots, R1 and R2, two different. It's implied that R1 is not R2 in the circumstance that we're describing here. So this is not equal to 0. since R2 is not equal, since R1 is not equal to R2. All right, and so we were all set. We were good in that section when we said that e to the R1t and e to the R2t, that those were different enough that we had all the solutions and that we could just say that this was the general solution. We were fine. We were okay. All right, next. How about when we went through and said that the general solution to ay double prime plus by prime plus cy equals 0 when the characteristic equation had complex conjugates, oops, alpha plus or minus beta I is y equals c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. Right? So we went through and we said that if we had the general solution of our second order differential equation, when the characteristic equation had alpha plus or minus beta I, we said that this was going to be the general solution. Now it's implied, if we're saying this is the general solution, that y1 here and y2 are different enough that they are going to get us all of the solutions. When we said that, we certainly did not have enough data to be able to support that. We did not have any logical argument to justify that. But now we do. We have a test. We can go through and we could calculate the Wronskian, and the Wronskian of y1, y2, it will tell us whether the two solutions are different enough. So let's go through and try it. All right, so I'm just going to use the same. I'm not going to rewrite it because this is going to be a big calculation, but I'm just going to use the same definitions here. y1, y2, y1 prime, y2 prime. All right, so we're going to have y1, that's e to the alpha t cosine beta t. Before I write any of the y2 stuff, I need to calculate the derivative, and it's going to be a long derivative here because the product rule. So we're going to have first times the derivative of the second, which is going to be beta sine beta t, negative beta sine beta t, plus cosine beta t times the derivative of the first, which is alpha e to the alpha t. Okay, so product rule on that guy. And now the second one, we're going to have e to the alpha t sine beta t. And now we need to do the derivative. So we're going to have e to the alpha t beta cosine beta t plus sine beta t times alpha e to the alpha t. All right, and now to go through and calculate the determinant, you're going to take this times this minus this times this. So when we multiply these two, we're going to have e to the 2 alpha t beta cosine squared beta t. This times this, we're going to have plus alpha e to the 2 alpha t cosine beta t sine beta t. And then we're going to have minus this times this minus. So when we do minus this times this, we're going to have a double negative. So it's going to give us plus. So we're going to have plus, and then we're going to have beta e to the 2 alpha t sine squared beta t. And then minus this times this. This time it's going to be negative. We're going to have alpha e to the 2 alpha t cosine beta t sine beta t. All right, if you take a look at that, this and this cancel. And so we're going to have beta e to the 2 alpha t cosine squared beta t plus beta e to the 2 alpha t sine squared beta t And then we could go through and factor out the sine squared plus cosine squared, which equals 1, and we'll end up with beta e to the 2 alpha t. And the question is, can this equal 0? Right? So for the Wronskian to go through and tell us that these two solutions are different enough that we're guaranteed that all the solutions are made up of these linear combinations, we have to have this not be 0. Well, what do we know about it? Well, if the general solution does have complex conjugates, then beta can't be 0. If beta is 0, then we don't have complex conjugates. You need to have the imaginary part to have complex conjugates. So this is, and of course the e to the 2 alpha t can never equal 0. So this is not 0 because beta is not equal to 0. It's required to have complex conjugates. Okay, last but not least, once upon a time we said the general solution to ay double prime plus by prime plus cy equals 0 when the characteristic equation had repeated root r was y equals c1 e to the r1 r to e to the rt plus c2 t e to the rt. Right? So when we got repeated root r, we said this was the general solution. So we went through and that implies that these two solutions are different enough that the combination of them will get us all of the solutions, that you can't find another solution that will satisfy the differential equation that is not in this linear combination. Now, at the time, we certainly did not have enough logic or argument to be able to justify that, but now we do. We can go through and we can calculate the Wronskian of y1 and y2, and that will give us a measure of whether they are different enough to get all of the solutions. All right, so Wronskian of y1, y2. The Wronskian is the determinant of the 2 by 2 matrix. So we're going to have e to the rt, and then the derivative of that is e to the re to the rt, and then we're going to have t e to the rt, and then the derivative of that is t times re to the rt plus e to the rt. And then the determinant, we get this times this. So that's going to give us t r e to the 2 rt plus e to the 2 rt minus this times this. That's going to give us rt e to the 2 rt. And if you look at that, these two cancel, and we're just left with e to the 2 rt. Can e to the 2 rt equal 0? The answer to that is no, not equal to 0. And so thus, the Wronskian does tell us that these two solutions were different enough that they got us all of the solutions to the differential equation. Okay, so we were justified when we got to this section and we said, you know what, these two, that's good enough. That's good enough. We've got enough solutions. We've got enough solutions to go through and find all of the solutions to the differential equation. It turns out that it was okay for us to do that. Okay, so that concludes the video on these second order differential equation theorems. I hope you enjoyed it. It's a long one. So I'll see you next time.